Good morning, everyone. Welcome to the research seminar for heavy-duty on-road vehicle inspection and maintenance program. This is our contract with UC Riverside CSERT. This research project, it's on the contract 15 RD022, and we just recently published the final report on the website. If you are interested in this program, please check the website as well. I will give a first of all, I want to give I have an emergency announcement just in case there is a fire alarm. Everyone should exit using the emergency exits. And if the fire alarm was on, we should wait in the Cesar Chavez Park, which is just across the street of this building. And I think that's it. So this project, we started this project back in 2015. And the background for this project is in the California State Implementation Plan, California still faces significant challenge in meeting air quality standard by 2031. The CIP indicated that additional NOx reduction is needed to meet the 75 ppb ozone standard in South Coast. In South Coast, the heavy-duty vehicles contributed about 35% of the total NOx emission inventory. And with existing programs, we won't be able to meet the 75 ppb standard by 2031. And therefore, we need more stringent control of NOx emissions, especially for heavy-duty vehicles. Diesel engines are, the emissions of diesel engines are controlled by after-treatment devices. The diesel particulate filter, DPFs, controls the PM emissions, and the selective catalytic reduction controls the NOx emissions. In the selective catalytic reduction system, the urea is decomposed to ammonia, and ammonia reacts with NOx to form nitrogen and water. Currently, in the state of California, there are some heavy-duty inspection and maintenance programs. One is the Heavy-Duty Vehicle Inspection Program, HDVIP, and the other one is the Periodic Smoke Inspection Programs. Both programs are based on the opacity measurement, and these programs focus on DPF and PM emissions, and there's no existing I&M programs for NOx emissions or the SCR system. The International Council on Clean Transportation published a review in 2015. That review examined all the heavy-duty I&M programs across different countries and the United States. In that report, all the tests of smoke opacity are based on old diesel technologies. Only Australia has an optional voluntary program that will test for both NOx and PM. So there's no previous experience for California. There's not much experience for California to learn from. And there are many potential technologies that can be used in heavy-duty I&M. For example, the onboard diagnostics and remote sensing devices and on-road plume capture devices, such as the portable emission acquisition system developed by ARB. And how do we use these different technologies in heavy-duty I&M is still an open question. And what are the emission benefits by fixing SCR-related malfunctions? That's something we have to learn from this project. And the objective of this study is to identify and evaluate various approaches and technologies for a more comprehensive heavy-duty I&M program in California. And in doing this, CSIRT performed a literature review of heavy-duty I&M programs and technologies, and then they measured the pre- and post-repair emissions at repair facilities in Southern California with a suite of instruments. And they evaluated the potential emission benefits and trying to understand the effectiveness of different options. And here are some additional information. If you are interested in this project, please check on these websites. And now, Thomas, all yours.
All right, thank you, Yi. Thanks for having me up, and excited to talk about some of the results from our program today. So I wanted to start off and acknowledge my co-authors here. Lots of people from UC Riverside, of course, but also we were working with Mark Carlock, who used to work with ARB and is now a consultant. And then we also had team members from West Virginia, including Nigel Clark. So a nice team to work with. So just a little bit of background, and some of this is somewhat of a repeat of some of the information that Yi presented. But in terms of understanding the importance of heavy-duty emissions, obviously it goes back to health and the health implications. You can see that the shaded areas here are ones that are non-compliant for ozone, as well as, and there's also non-compliance for PM. And of course, NOx that comes from heavy-duty mobile sources is a critical component of the formation of ozone. And NOx also contributes to secondary PM as well. So it's a very, very important in terms of improving air quality to understand where these emissions are coming from. Getting a little more specific, if we look at the Los Angeles air basin in particular, you can see that there's been significant progress when you look at the progress from a base case scenario to where we need to get to in 2023. And the solid bar here represents the goals that need to be made in terms of reductions of NOx emissions. And the red circle there indicates the mobile source contribution. So you can see that even if you totally eliminate the mobile sources, you're still going to have a very challenging goal to meet the air quality standards in 2023 and 2031 in Los Angeles. So it just kind of outlines how important it is to really bring NOx down to very low levels, and also just the difficulty in doing this task when you look at it from that perspective. Looking at NOx emissions from heavy-duty vehicles, you can see that on the left side of the screen, this just shows some in-use chassis dynamometer data, and the green bars here represent the actual measurements that were made, and then the red bars indicate where the standards are. So, whoops. So obviously good news in that those green bars are going down, but you can also see that the discrepancy between where that red line is and where the green bars are as a fraction or as a percentage goes up. So what we're seeing is that the in-use emissions are higher than what we might expect based on what you might hope to get from the certification standards. On the right side, this shows MFAC projections of the difference between what you might want to have based on a 0.2 standard for NOx versus based on what the expectation is that the emission rates from the heavy-duty vehicles will be. And you can see the blue line is quite a bit higher than the red line. So now background more specifically in this particular heavy-duty inspection and maintenance program. So here, E showed 35% contribution of NOx. And currently, if you look out to the 2025 timeframe, that number is going to slightly change to about 24% and 10% of PM, but it's still going to be a relatively significant and important number. As we heard, California has a couple of existing inspection programs, the heavy-duty vehicle inspection program, and then the periodic smoke inspection program. Both of these are based on SNAP acceleration opacity testing or sort of engine control label checks, but there's not really any significant controls of NOx emissions. And also they don't necessarily account for the newer after treatment that has been on the heavy-duty vehicles since 2007, although recently the opacity has been reduced to a 5% level. So there's been some effort there, but still in terms of NOx, there's nothing existing in place. You know, taking all those factors into account, you can see that you know, there is at least a need to look for a more comprehensive heavy-duty inspection and maintenance program to ensure that emission reductions are going to be maintained in use and over the lifetime of the vehicle to get kind of the air quality benefits that we're looking for. So the objective of this study was to evaluate and kind of assess options to get to that point where we're looking for a comprehensive heavy-duty I&M program that could be implemented into California. Again, probably looking at somewhere around the 2025 timeframe. So 3 main tasks for this project. The first task was a literature review where we looked at kind of ongoing heavy-duty I&M programs as well as different technologies that could be utilized in a program going forward. Then we looked at and did a sort of a prototype or pilot program where we evaluated a number of different technologies and looked at their potential effectiveness. And then we kind of put all these things together to make some recommendations. So the literature review here, and you know, we looked at a number of different things. We wanted to look at the framework for what an I&M program might look for, and look at different types of techniques that could be used in terms of what pollutants they might measure, how they might diagnose and understand what the issues are, you know, and what would be the specific test methods, or if you had a chassis dynamometer, what the cycles might be. And then we evaluated and looked at some of the methods specifically in the literature review before we started our test plan. And so some of those were tailpipe measurements, anywhere from chassis to PEMS, portable emissions measurement systems, to plume measurements like RSD, and then also OBD was another critical element of that. So this is just a summary of some of the things that we found in the literature review. So looking from left to right here, the first column talks about what methodology it is. The second column is the pollutants. The third column sort of talks about the practicality of the measurement in terms of ease of use and time constraints. And then the fourth column talks a little bit about the capital costs that might be associated with these different measurement methodologies. So for the first two, this is chassis dyno and 1065 compliant PEMS. These methods are obviously fairly comprehensive, but some of the capital costs on these methods, if you look at the far right column, are fairly expensive, and the number of vehicles you can get in approaching those with those methods at a point in time is smaller. So it's going to be very difficult to capture all million trucks that come in with these methods. Mini-PEMS are obviously advancing. They're smaller versions of the fully compliant PEMS. Lots of progress has been made in that area. Capital costs are a lot lower, but again, in terms of basing an entire I&M program around the mini-PEMS, that's probably, again, a difficult thing just to get all the vehicles. Remote sensing, obviously you can get quite a few more vehicles in an application where you are driving vehicles through a remote sensor or a tent or plume measurement system. The costs are reasonable given the amount of vehicles you get, but there's other methodologies that we think provide some even better benefits. And so moving on from the tailpipe measurements, now we want to talk about the OBD measurement methodologies. And so here, obviously OBD has been implemented starting in 2013. All the vehicles are supposed to be compliant or at least largely compliant and having OBD devices. And so the advantage here is that you've got a system that is already incorporated into the truck. So a way to monitor really all 1 million vehicles once the fleet turnover gets to the point where you have mostly these vehicles. So you can do it in several different ways. You can go to a repair station. You can have a kiosk where you just, the driver comes up, plugs into a kiosk, and this is done in several light-duty programs in different states across the U.S. And then you can also have different ways of transmitting or doing remote OBD, where you can either do a Wi-Fi transmission, or you can do a cellular transmission where you can continuously monitor the system. So the advantage here is that you measure a pretty wide range of system components that can potentially give you problems, and you can measure them continuously. So that certainly is an advantage, and this certainly is going to form the basis for the heavy-duty I&M program. So based on that information, we wanted to try to do a pilot program that captured the essence of as many of these elements as we could. So one of the things that we wanted to do, and really the cornerstone of this, is that we wanted to understand repair effectiveness that was happening. So we did a program where we brought vehicles in. We actually went to a repair station, or actually two repair facilities, although the majority was done out at a single large volume repair facility. And basically we looked for vehicles that had the check engine light on in particular target areas that I'll be getting to in another slide here. So we characterized the emissions before and after using just a repair grade heavy-duty chassis dynamometer. So both facilities had a repair grade chassis dynamometer that we were able to run a variety of different conditions. So we looked at 30 miles an hour, 50 miles an hour, idle and high idle. And we used kind of repair grade analyzers or I&M grade analyzers for some of our measurements there in the program. And then the OBD scans here was really the centerpiece of this part of the program, in that we were bringing vehicles in based on the information provided from either the mill or the OBD scan. We had a variety of other instruments, sort of the so-called mini-PEMS instruments that were included in this trial. And so we kind of wanted to understand how those might work and how effective they might be. We also looked at some of the plume measurements or remote sensing type of systems, the heat EDAR system, which is an RSD system, and then the ARB peak system, which is kind of a plume capture type of system. So the target here was 50 vehicles, looking for about an 80-20 split, with 2013 and newer vehicles being the predominant source of vehicles that we were looking at. And you know, in terms of the timing for the program, it was about late 2016 to early 2017. So, you know, the 2013 and newers became more frequent as we went through the program, but remember, those were fairly new vehicles at the time the program actually was done. So here is the test matrix that we developed, and there was a couple of different sources that we used to develop this, and we worked in conjunction with ARB to develop this matrix. And basically we scanned about 2 years of repair records from the primary repair facility. We combined that with MFAC estimates of failure rates, and then we also looked at, or ARB looked at, some of the durability vehicle data that they had. So a combination of all these gave us our target matrix of vehicles that we were aiming for. So the first column here with the numbers in them is the target that we were shooting for. The second column is the number of vehicles we identified in each of these different categories. And we had some vehicles that came in a couple of times, and some vehicles that started out the program and for one reason or another, they didn't complete the program. So you know, they found out that something bigger had to be done on their vehicle, and so they grabbed the vehicle and headed home. You know, and then a couple of them, they had to come back for some subsequent repairs. So in total, we had 47 vehicles and 51 individual repair sequences, because some vehicles came back multiple times. And 2 of those vehicles were Navistar non-SCR equipped vehicles. And you know, based on the results and just thinking about that 2025 timeframe, we didn't feel that those were probably the most representative in terms of what we needed to do in looking at a heavy-duty I&M program. So we have excluded those data from the rest of the results, although they are in the final report. So just to give you an idea of what we did here, this is a picture of the truck, of one of the trucks on the chassis dynamometer at one of the repair facilities. And so we went through a sequence of operations on the vehicle. We warmed the vehicle up from 3 to 5 minutes at 60 miles per hour, and then we did a lug down test to kind of ensure that the vehicle was warm enough. We also monitored some of the NOx emissions during that time as well, to kind of make sure that we were getting, we weren't, extravagantly in this cold start or in a cold mode here. Then we would operate the dyno at 50 miles per hour, but really what we were more targeting is 200 horsepower, because this is a water brake dyno, and it's based more on horsepower, and that gives us a test point that was near the top part of the engine map. So that was one test point. Then we bumped it down to 30 miles per hour, which was 100 horsepower that we were looking at. And at each of those points, we held the emissions there, or we collected emissions as steady as we could for a minute time period. Then we dropped down and did two different idle conditions. One was just a normal idle, and then a high idle at 1800 RPM. Then we followed that with a snap and idle opacity test. So just to give you a little bit of a perspective, obviously people think about dynos. We oftentimes have the luxury of transient dynos where we can very specifically mimic speeds and things for exactly for however long we want. This is a water brake dyno, so you're having to play with things a lot more to keep the conditions steady. So really the goal of this was not to quantify whether a truck was at 0.25 emissions versus 0.2. It was really to determine, do I have a really high emitter, and am I bringing that really high emitter to very low levels after the repair is made? So this just shows the range of instruments that we used here in terms of some of the different systems that we had here. And so some of the mini-PEMS information, I'm not going to talk about it in great detail today, but that's talked about fairly more extensively in the report. So the instrument in the top left corner was the MAHA instrument that was kind of the primary instrument that we utilized for the measurements. We also did some comparisons between EDAR and the PEAK system, and so again, that information is also not going to necessarily be the focus of the talk today, but it is discussed in more detail in the report. And so here with the EDAR system, you have a laser light that shines down that is able to capture the plume. And then for the PEAK system, which is the ARB system, you're able to capture the plume with one of two intakes that can either sample exhaust from tailpipes that are extended up or extended down. And you can kind of see the layout in the repair system, the repair facility at the very bottom. So I think we had probably 50 to 100 bays in this repair facility. So it was very, very large repair facility that we were working out of. Okay, so let's go ahead and move on to the results. So again, this is with our MAHA instrument. And here shows the results at 30 miles per hour for the 10 highest emitting vehicles that we measured at 30 miles per hour. So just kind of to give you a roadmap of what the what the graph is showing here. The red bars indicate the pre-repair emissions for each vehicle. The green bars indicate the post-repair emissions. And then across the top, these blue triangles represent the reduction rate of the emissions that we saw for each of these particular repair sequences here. And then along the bottom, the notation there includes the vehicle model year, and then the A signifies what manufacturer that is, and then the 1, 3, or 5 here indicates when the vehicle was brought in. So the first 2011 vehicle from manufacturer A that was brought in is 2011 A1. So what you can see here, several different things. You can see that on grams per brake horsepower hour units, many of the vehicles did have emissions that were well above what one might want for a certification standard of 0.2. Now, we don't want to just totally say that every vehicle here was a super high emitter. If you extend this graph beyond these first 10 vehicles, you go out to about the, you go out to about 20 vehicles. They are still above the 0.2 standards, but about 29 of those vehicles actually had emissions that were at or below the 0.2 standards. So not every vehicle we're seeing is a super high emitter. And remember, we're targeting super high emitters here. So in terms of the pollutant, or the different repair types, quite a range of different repair types that we saw here. Some of them, injector doser was pretty significant, or seen quite a bit among the highest emitters. But we were seeing a pretty wide range here, an exhaust pressure sensor, issues with the turbocharger. Some of these are DEF issues, turbo speed sensor. So really not one single issue that's contributing to the NOx emissions that we see for any of these. And I think one of the conclusions that we've drawn from this study is the complexity of these repairs, and that oftentimes there are multi-components are involved, and that the different codes can lead to multiple different repairs that might be needed to bring the vehicle back into compliance. So also, if you compare the red and the green bars, you can see that in many cases, particularly for these high emitters, we're seeing good emissions reductions. And if you look at the matrix overall, 22 of the 49 vehicles showed greater than 80% reductions. So very good reductions, even as you're starting to get to that lower end of the vehicles in terms of emission rates. Okay, now let's go to the 50 mile per hour results. And so again, kind of the same layout here. And again, what you see is that there are certainly emitters that are higher than the standard here. Again, you extend this out beyond the first 29 vehicles. We had 29 that were above the 0.2 gram standard, but again, 19 of them were not. So we're seeing high emitters, but we're also seeing some that are more in the maintenance category or preventative maintenance going forward, that we don't necessarily capture the benefit of those just simply looking at a graph like this. Here again, fairly high reductions based off of this axis over here. About 15 of the 49 vehicles had greater than 80% reductions. And many of these vehicles, if you look at many of these vehicles, like the first 3 here, and I think this one here, those were all found to have high emissions at both 30 and 50 miles per hour. So definitively, we're identifying vehicles that are having issues in getting repaired here. So again, some of the same problems with injector dosers, add in an EGR cooler, some DEF issues, some issues with turbochargers, but again, not one single issue that can be used to characterize where we're seeing all of the high emissions. Okay, I do want to just briefly talk about some of the mini-PEMS systems here. And so this shows two of the mini-PEMS systems. One on the left is the NTK system. The one on the right is the 3DAT-X system. And smaller data set obviously on the right side. But what we are seeing is that for the NOx emissions, it does appear that the mini-PEMS will have some capability for identifying these high emitters. And so that's something that we can use looking into the future. Okay, so let's just summarize the results from the NOx emissions here. And what we find here is that there are a number of these vehicles with OBD, with mill lights on, that are above, that are emitting at higher than one might expect based on the standard for one or both of the 30 to 50 mile an hour tests. If you look at those NOx reductions, pretty significant. About 45% of the vehicles tested, or the repair sequence, provided greater than 80% reductions at 30 miles per hour, and about 31% also provided reductions at 50 miles per hour. And if you look at the highest emitters, those generally showed very large reductions under all of the different test conditions. Let's see here. So we also looked at the fleet average emission reductions, and here we identified two different statuses. All the vehicles came in with the check engine light. We also looked at the subset of vehicles, as was slightly different, where the DM1 mill was on. And you can see that the fleet average reductions here ranged anywhere from 81 to 46% if you look at the entire fleet. And then finally, we see that the mini-PEMS did show a potential to identify high emitters. So moving on to PM, and I'm going to highlight the opacity results here. And what you can see here is that if you look at the 5% threshold and sort of carry that across, 7 of the vehicles had opacity emission rates that were greater than 5%. So that's the current threshold. So a lot of the vehicles actually didn't show super duper high PM emissions. We weren't necessarily targeting high PM emitters, and you have to also consider that even a vehicle that might be having a fault related to PM emissions, if the DPF is trapping the PM still, you may not see the benefit of that strictly from an immediate test that's done immediately right after that. So again, if you look at, and actually the second and the fourth vehicle are the same vehicle, it just actually came back for a second repair about a week later. And you can see that all of the SCR-equipped vehicles that had opacity emissions greater than 5% ultimately were repaired to the below 5% opacity level. And again, if you look at the range of issues here, you can see that there's a pretty diverse range of different things that was happening with these opacity or high opacity emitters, again, just kind of building on that theme of how complex things are in terms of understanding the repair effectiveness. Looking over the fleet as a whole, we had about 11 vehicles of the 49 that even though the PM emissions were not necessarily all high, we did see 11 had 80% or greater reductions. So summary for the PM emissions, if you look at this suite of instruments that we looked at, we actually found the opacity measurements showed the most consistent PM reductions, and that's discussed a little bit more in the report itself. Looking at the pre-repair SCR-equipped vehicles, remember we did throw out the Navistar non-SCR vehicles. The ones that came in greater than 5% when they completed the repair sequence all were below 5% in terms of opacity. And if you look at the fleet average opacity reductions, it was about 43%. We did do a number of other mini-PEMS system. We didn't find the consistency in this particular study between all of those different results. They do certainly appear to show greater sensitivity probably than opacity, but we think there might be more work needed in that area, or a different kind of study, because we really weren't targeting just something to look at high PM emissions. Okay, so moving on, just want to kind of talk a little bit about the repair costs here. And you can see from this slide here that there's a pretty wide range of repair costs, anywhere from simply sensor replacements, which were part of the test matrix that we looked at, to bigger issues where you're wind up, say, replacing a DPF, or you're replacing a turbocharger, where the costs were more substantial. So this is the second half of the vehicles, and again, a pretty wide range where, again, you're going from replacing the SCR to major repairs on to other repairs that are below $1,000 for maybe sensor replacements or something like that. So on average, we were at about $2,000 for our repairs that we saw in this particular study. We also looked at the broader repair records over about a 2-year period at the major repair facility. And here you can see that a lot of the repair categories are in the ballpark of several $1,000s, although there are a number of categories like the turbocharger, NOx, which a variety of things might fall into this category, fuel pressure or fuel system and engine, that would have higher emissions. And sort of these categories here, we tried to pick them to be consistent with some of the categories that are in the MFAC model. So looking at just a summary of the repair costs, you can see that there was a pretty wide range from sensor replacements to really major repairs. Looking at some of the categories, when we look at those target categories that we had in that initial test matrix, some of the higher ones were the ones that could include the major repairs of DPFs, SCRs, or turbochargers. Again, average costs were roughly $2,000, which was relatively consistent with the repair costs from the repair records, with the exception of some of these major categories where you're going to get higher costs. So where does that all lead in terms of what are we thinking about in terms of a comprehensive heavy-duty I&M program that could be implemented, in, say, the 2025 timeframe? Well, if you look at OBD, which was kind of the primary method we looked at in our pilot study, you know, a lot of the fleet by 2025 is going to be OBD equipped at that point in time. So certainly that could be a cornerstone of a comprehensive heavy-duty I&M program at that point. Obviously, the ability to monitor many different components at the same time under the full range of operation is a key component there. The fact that OBD is you know, a test can be administered fairly quickly, or even through a remote or wireless or cellular type of system, makes it much easier system to implement than something that requires a lot more downtime for the vehicle. So as a primary method, we certainly thought OBD would be a centerpiece for a heavy-duty I&M program. So what else might you want to have in a heavy-duty I&M program? And you know, you look at the next stage of that would be that as you know, OBD may not necessarily capture all the vehicles that maybe the older vehicles that don't have the OBD system implemented already. And so there are also you know, checks and balances to make sure that there aren't failures that are being missed by the OBD system that would otherwise lead to higher emissions. So we suggested coupling the OBD with some type of RSD program, and whether that's a strict RSD, an ohms method, which is basically driving vehicles through a tent, or peaks type of system, which is essentially a PEM, a plume measurement system. Some type of system in this area could certainly be used to supplement this. This would eliminate the need for the trucks to necessarily go to a centralized facility, as you could set it up hopefully in areas like weighing stations or other areas where you have high heavy-duty vehicle traffic. Again, still some limitations when you look at RSD type of systems, in that they only see the operation of the vehicle for a very short period of time, so you could easily miss high emissions. You might also have somebody that's you know, that's frustrated and drives through in some erratic manner that might create high emissions that would not otherwise be seen. So so those are some of the disadvantages. So adding yet a third component to this, you know, we think at a smaller level, the mini-PEMS could also be involved here, because again, there might be some situations that are too complicated to interpret based on either OBD, RSD, or even those two systems together. So you could have the mini-PEMS as a system that could be utilized to kind of verify some of the effectiveness of the other two systems, and to look at, you know, if there were situations where you know, someone didn't feel they had high emissions, you could verify it with yet a third technique. And you know, also again, as the mini-PEMS continue to progress, which we certainly expect them to in the next 6 years, you're going to get continuing improvements in this area as well as the possibility of you know, improving the sensitivity on the opacity measurement. Okay, so just in summary, you know, CARB is looking to put in place a more comprehensive heavy-duty inspection and maintenance program, and you know, looking at all of the data and the literature review, you know, it appears that an OBD-based program could provide benefits in both NOx and PM emissions, And again, just looking at our fleet average emissions, we found anywhere from 46 to 80% reductions for NOx, and for opacity, 43%. And I think the other thing that's not in those numbers is that we probably have also captured maintenance issues that are preventing emissions that may go to higher levels at some point that just haven't quite got there yet. So again, a tiered approach to an I&M seems like it would be a good place to go, obviously starting out with OBD as a basis, but coupling it with other types of systems. And if you look at sort of trying to achieve those reductions in NOx that you're going to need to meet the air quality levels, you know, one could certainly see that I&M would be a critical component of this, in that, you know, not only are you going to be catching the vehicles up front with a certification test or even an in-use test with PEMS on a small number of vehicles, you're really going to probably be able to get significant and tangible emissions benefits over a pretty wide range of the in-use fleet. And there's more work ongoing to kind of quantify this. Obviously, we were at a repair station. We were bringing in vehicles that preferentially had the check engine light on. ARB is doing more work in this area with roadside pullover studies. I think their current rate is about 11% of the vehicles they're finding with an OBD code or check engine light on. So again, definitely if you look at those types of reductions over that percentage of the fleet, it could be an important part of doing that. And UCR is also involved with Eastern Research Group on some of those studies. So with that, I think I'll close and open it up for questions.
Thank you, Tom. Any questions?
Hi, Tom. Very nice presentation. Johan Herner with the Research Division of the California Air Resources Board. There was a couple of slides where you showed the reductions to PM and NOx after repair, and sometimes the reductions were very great and sometimes they were not. I guess generally you would expect if a truck came in with the mill light on and the repair needed was associated with NOx, and then you did the repair, you would get NOx reductions. And if the mill light was on, something associated with the DPF, then you would get reductions in opacity. I didn't really see that in that graph. I was trying to correlate, you know, the reductions with the type of repair. And sometimes you saw almost 100% reduction because you cleaned the DPF, or you got great reductions in opacity when you fixed the dosing harness or something like that. I was wondering if you had done any work around that or had any thoughts to that.
Well, certainly, I mean, you can look at looking at the whole 51 repair sequences. We only showed 10, the 10 highest here. You can really see that the systems are very sophisticated these days. There is a lot of, there's not simple answers, or at least there weren't in our study, as to, you know, if you bring a vehicle in with a particular problem. Some of the vehicles, for example, that had high NOx emissions also had high PM emissions. You know, many of the vehicles that had high NOx emissions did not necessarily have issues that you would intuitively associate with high NOx emissions. So I think one of the conclusions that I draw from this data is that you know, there is perhaps a simplistic view that we've been looking at these repairs, but when you get out in the real world, it appears things are fairly complicated in terms of, you know, where these are coming from. where these repair benefits are coming from.
Yeah, it would certainly be.
I hope that answered your question. And not
Yeah, sort
avoided
of.
it.
I mean, it means that it is a big, complicated system, and even if when you're trying to quantify the emission reductions you get out of this, just by interacting with the system, and even if you repair something associated with the DPF,
Yeah.
your work seems to suggest you might be getting NOx reductions as well.
That is correct. Yeah.
Thank you.
And also, I think, again, the other part of that story is also the fact that, even if on those vehicles where you're not seeing the huge reductions, you might have intercepted a problem that's going to occur in the next 3 months or the next 5 months.
Questions?
Hi, Tom. James Goldstein. Do you have a sense of the level of training or experience that the technicians had who were working on these repairs? And did they have any particular challenges as they were doing the diagnosis? Did they get it wrong, have to go back and start again?
So the repair systems, we had one OEM repair facility and one non-OEM repair facility. But the majority of the repairs were done at the non-OEM repair facility, just because of the volumes. And in most cases, we worked with the technicians, not assisting them with the diagnosis, but trying to understand where those diagnoses were made. In most cases, it seemed like, the pathways they were taking were reasonable. Of course, we did see there was several cases where the vehicles had to come back after the fact. There were also some cases where the emissions were not, we talk about how many had the good reductions. There were also, as has been pointed out, there were also cases where the reductions weren't found. So again, I think that's, you're starting to get into electronics where sort of that you have a little bit of a feel for what might be going on, but talk to somebody about, the NOx emissions are increasing, and it might not be intuitively obvious to everyone what that might mean. Which again, that sort of going back to that OBD and having that basis, you take away that OBD framework and you just bring vehicles in and you say, we caught this with an RSD, or we saw it, there might be no feel for where you can diagnose that.
This is William Leung with ARB. So if I understand correctly, what's being shown is that if a repair is done, there are benefits as measured by OBD. But in terms of structuring an INM program, does your work kind of point to specific types of repairs that should be prioritized, or kind of like timing or anything like that?
We didn't find any. We found that there were a full range of repairs, a lot of different types of repairs that were giving us those 80% or greater reductions. So certainly, like injector doser problems, we probably saw those as many in as many of the cases as any other, but I don't think we found a specific repair that really was the catch-all be-all, or one or two repairs that were the catch-all be-all. In terms of the timing, a couple of different scenarios depending on how you might implement OBD. If you have a system where you're just plugging into a kiosk, you're probably going to be limited to once a year type of timing. If you go to something where you have a remote OBD, where it's either a Wi-Fi connection or a cellular connection, you could certainly have that done on a more frequent or continuous basis going forward.
Hey, Tom. Jason O'Falkenfell here. Can you just clarify for me in terms of how the repairs were done? Were they mostly still the repair shop would give the owner a recommendation, but the repairs done were still at the discretion of the owner? So, for example, they could have been more concerned about just solving, let's say, get me out on the road as quickly as possible, irregardless of the actual emission problem. So in terms of the emissions, you're seeing here a potential I&M program that forces, let's say, a vehicle to clear the mill to clear the whole problem would actually potentially get more emissions benefits than what the study is showing here?
Yeah, so here, you know, obviously there was the interaction between the owner and the repair shop was something, I mean, we were somewhat knowledgeable of what was going on there, but we didn't intercede in that process. There were some cases where the repair shop told the owner that the repair was going to cost a certain amount of money, and that was too much for that person, and they left. So there were 2 or 3 vehicles where we started the repair sequence, and then the vehicle owner, the owner driver took off, and we didn't finish it. There were a couple of cases where, you know, the repair sequence wasn't necessarily completed, in that the vehicle owner left, and we found that the DM1 light was still on. So we tried to exclude those. If you look at these fleet average numbers, we did exclude a few cases where the repair would not be complete from an I&M perspective to get these results here.
Tom, you had information about the unit cost for each vehicle for repair. I was wondering if you extrapolated the data and, you know, based on the failure rates or, you know, repair rates for the entire fleet, and estimated what it will take to, you know, fix the super emitter issue and for the entire fleet, and what the unit cost for ton of reduction would be.
We did approach some of that and went back and forth with ARB on trying to do some of those estimates. You know, in the end, we didn't think that we had enough information to accurately make those estimates. So we didn't wind up including that in the final report. And some of the issues are, you know, just simply the rate at which check engine lights are coming on in the fleet. There really isn't, that data set is building up now, but it wasn't really available at the time period that we were doing the study. So I think ARB is gonna obviously look at that in a lot more detail. And we sort of scratched the surface there, but we didn't feel that it was strong enough that we could really go out and make those estimates appropriately.
We have a few questions from online. The first one is from Michael Baker, and he's asking about slide 25. What is the difference between the check engine light and DM1 mirror light?
Okay, so the check engine light, you know, the check engine light, there is a, we don't have an absolute definitive answer on the differences between the check engine light and the DM1 mill light. You know, the check engine light's supposed to come on at a certain time period, and once a certain sequences of an issue occur, there should be a stored DM1 code, mill code. We did see some differences there that were probably larger than we expected. We expected that of the check engine light vehicles that came in with check engine light, we probably expected more of them to have the DM1 mill on. You know, a couple of different reasons for that. I mean, it might be that you know, this version of the Silver Scan was a little bit older, and you know, you know, the HEM data loggers weren't necessarily optimized for doing that type of work. We're continuing to improve to work on that, but there still is some uncertainty actually with regard to that question.
The second question is from Riza Kavian. Did you also look at the emission from construction heavy-duty equipment? Are you aware of such studies or the significance of the problem?
We did not look at construction equipment. And obviously, construction equipment is you know, not as advanced as the on-road studies, or as the on-road technologies in terms of implementation of OBD and things of that nature. So I'm not necessarily aware of anything that's specifically done for off-road that's similar to what was done here.
The last question is from Gary Bishop. Did the repair shop have a blank check for repairs? Did you follow up some time later with the repair trucks to see if the repair reductions lasted?
So no, the repair shop did not have a blank check, and in terms of doing that, that interaction was entirely between the owner and the repair shop. Again, we sort of, in terms of the quality of the repair, we judged that based on whether the DM1 mill and the check engine light were off, excuse me, when the repair was completed. And unfortunately, we weren't able to follow up as much. The repair shop closed down shortly after our study. As a matter of fact, the month after our study, so I got very lucky. So we probably had a few open questions that we weren't able to get answered.
All right, any other questions from the audience? Okay, I think that's it. Thank you all for coming to this seminar. Thank you, Tom.